Good morning, everyone. Welcome to the intermediate project presentation for our course, Computer Vision 23 AI 301. I am presenting on behalf of Group 11. Our team consists of 4 members, Arjun Murali, Nithin Prakash, Abhishek Ranjith, and Devaduthan V. Our project is titled Automatic Image Caption Generator using Deep Learning. Today we will be walking you through our Phase 1 implementation. The goal of this project is to build a system that can automatically describe images in grammatically correct sentences. This is a vital task that sits right at the intersection of 2 major fields in artificial intelligence: computer vision and natural language processing. Let's start with a brief introduction to what we have built. In simple terms, we are teaching a computer to see and speak. We are developing a deep learning-based system that takes an image as input and outputs a descriptive caption. To achieve this, we are using a hybrid architecture. We use convolutional neural networks, CNNs, to extract features from images, essentially helping the computer see, and long short-term memory networks, LSTMs, to generate the corresponding text sequence, helping the computer speak. For this phase of the project, we focused our experimentation on the Flickr 8K dataset. We have successfully completed the pre-processing, model implementation, and baseline testing. Our early results highlight the model's ability to generate basic descriptions and have given us crucial insights into challenges like handling rare words and aligning visual features with text sequences.
Now let's define the problem and understand why this project is significant. We are currently living in an era of visual data explosion. Every day, millions of images are uploaded to social media, digital archives, and assistive platforms. While humans can look at a photo and instantly understand the story it tells, to a computer, that photo is just a grid of pixel values. There is a massive gap between visual data and semantic understanding. The problem we are addressing is how to bridge this gap. We need a system that can translate visual signals into natural language. Our motivation for this project stems from 3 key applications. First and foremost is assistive technology. This is the most impactful use case. For visually impaired individuals, the digital world can be inaccessible. An accurate image captioning system can act as a visual interpreter, describing the world around them or the content on a screen in real time, significantly improving accessibility. Second is efficient image retrieval. Currently, search engines rely heavily on manual tags or surrounding text to find images. A captioning system allows for automatic indexing, meaning we could search for images in large-scale databases based on their actual content, even if no one has manually tagged them. And third is enhanced user interaction. By enabling machines to understand visual context, we pave the way for smarter AI assistants that can discuss visual content with users, creating a more intuitive human-computer interaction model.
Data is the fuel for any deep learning model. For our Phase 1 implementation, we selected the Flickr 8K dataset. Why did we choose Flickr 8K? It offers the perfect balance for an intermediate project, as its size is manageable for initial experimentation. It contains 8,000 images drawn from varied everyday scenes, including people, animals, and both indoor and outdoor settings. Crucially, each image in this dataset is annotated with 5 different reference captions. This is vital because it teaches the model that there is no single correct way to describe a scene. It allows the model to learn meaningful associations about objects, actions, and scene context, rather than just memorizing rigid labels. Before feeding this data into our model, we applied a rigorous pre-processing pipeline. For image processing, we had to standardize our inputs. We resized every single image to a uniform 224x224 pixels to match the input requirements of our CNN. We also normalized the pixel values to a range of 0 from 1 to ensure faster and more stable convergence during training. For text processing, we followed several steps. First, we tokenized the captions into individual words. Then, we converted all text to lowercase and removed punctuation to reduce noise. To handle computational constraints, we built a vocabulary containing only the most frequent words, for example, the top 5,000. Any words outside this vocabulary were mapped to a special unknown token. Finally, we mapped these words to integer indices and padded all sequence to a fixed length to allow for batch training.
Now let's dive deeper into our proposed approach and architecture. We adopted the standard encoder-decoder framework, which is the state-of-the-art approach for this task. For the encoder, we used Inception v3, a powerful pre-trained convolutional neural network. We didn't use it to classify images. Instead, we removed its final classification layer and used it solely as a feature extractor. As an image passes through the layers of Inception v3, the network identifies progressively more complex features, from simple edges and textures in early layers to complex shapes and objects in deeper layers. The final output of this encoder is a fixed-length embedding vector that represents a compressed summary of the image's entire visual content. For the decoder, we used an LSTM, long short-term memory network. Why an LSTM? Because standard neural networks can't handle sequences. They don't have a memory of the past. LSTMs are specialized recurrent neural networks designed to handle sequence data. The LSTM takes the image embedding vector from the encoder as its initial input. Then it generates the caption word by word. At each time step, the LSTM predicts the most likely next word based on two things: the visual context of the image and the sequence of words it has already generated. This allows it to maintain grammatical coherence over a sentence. The entire system is trained end-to-end using categorical cross-entropy loss, which teaches the model to minimize the difference between its predicted words and the actual words in the ground truth captions.
Let's discuss the results of our Phase 1 experiments. We evaluated our model using both quantitative metrics and qualitative observation. Looking at the metrics table, our object detection accuracy stood at 78.4%. This metric measures how well the Inception v3 encoder captures essential visual features. A high score here confirms that our eyes, the CNN, are working correctly. The caption generation relevance was 72.6%. This measures how semantically relevant the generated words are to the image context. The overall captioning performance of our baseline CNN LSTM model was approximately 75.1%. These numbers tell us that the architecture is functional, but there is significant room for improvement. Qualitatively, the preliminary implementation produced promising outcomes. The CNN encoder successfully extracted rich visual features, which the LSTM decoder used to generate short, coherent captions. When we fed unseen images into the model, it successfully identified primary objects and actions. For example, it correctly generated captions like "a man riding a horse" or "a dog running in a field." The model demonstrated that it has effectively learned to capture high-level visual semantics. However, we also observed limitations. The generated captions were often simple but contextually relevant. The model sometimes struggled with deeper contextual understanding and grammatical fluency, occasionally producing repetitive sentences. This grammatical stiffness is expected in a baseline model and is something we aim to address in the next phase.
Welcome back. In this section, we'll move beyond the raw numbers and dive into a qualitative analysis of our Phase 1 results. We wanted to see not just if the model was working, but how it was interpreting different types of images. We tested the model with a variety of scenes to evaluate its ability to identify objects, understand actions, and capture the general context. Our first example is this image of a man on a horse. The model's generated caption was simply "a man riding a horse." This is a great success. It accurately identified both the primary subject, the man, and the core action, riding. This demonstrates strong object recognition and the ability to associate the correct verb with the visual scene. Next, we have this vibrant image of a dog. The model outputted a dog running in a field. Again, it's spot on. It correctly identified the animal, its action of running, and the environment. This shows a basic but effective level of contextual understanding, linking the subject to its surroundings. For our third example, we presented a more complex scene with multiple subjects. The model's caption was children playing. This indicates an ability to recognize multiple entities, the children, and summarize their collective group activity rather than getting lost in individual details. First, the model has proven it can successfully extract rich visual features from an image. It's not just seeing pixels, it's understanding core content. Second, as we saw, it consistently identifies primary objects and actions correctly, like the man riding or the dog running. This shows effective visual grounding, where words are correctly linked to visual elements. And finally, it demonstrates a promising ability to learn high-level visual semantics, translating complex visual data into understandable, albeit simple, concepts. The captions are often quite simplistic. While correct, they can lack deep contextual understanding or fail to capture nuanced details present in the image. Furthermore, we've noticed the model occasionally struggles with grammatical fluency. It sometimes generates repetitive or uninspired sentence structures, especially when dealing with more complex scenes that require more descriptive language. In conclusion, Phase 1 has provided a strong foundation. We have a working baseline that understands the what and who in an image. Our next steps will focus on improving the how, enhancing the model's ability to generate richer, more grammatically complex, and contextually deep descriptions. Thank you.
Finally, I want to highlight the difficulties we faced in our future roadmap. The biggest challenge was handling rare and out-of-vocabulary OOV words. Our training vocabulary was limited. When an image contained a rare object or action not in our top frequency list, it caused the model to generate incomplete or inaccurate captions. We mitigated this using vocabulary thresholding and unknown tokens, but it affects caption richness. Another challenge was feature alignment. Bridging the static, fixed-size vector output of a CNN with the dynamic, sequential input of an LSTM required precise reshaping and embedding alignment to ensure consistent data flow. Lastly, computational constraints were a major factor. High training costs and limited GPU resources restricted our batch sizes, number of epochs, and ability to perform extensive hyperparameter tuning, which slowed down model convergence and optimization. In conclusion, Phase 1 of the project has been a success. We have built a functional end-to-end pipeline. We collected the dataset, completed pre-processing, and trained a baseline CNN LSTM model. We verified that the CNN extracts valid features and the decoder produces relevant text, confirming the feasibility of our architecture. Moving forward to Phase 2, we have a clear plan. We will implement attention mechanisms, which allow the model to focus on specific parts of an image dynamically when generating each word, rather than relying on a single static summary. We also plan to explore transformer-based decoders, which are known to generate much more fluent and complex text than standard LSTMs. Thank you for your attention. This concludes the presentation from Group 11.